Okay, so we were taking the limit as h approaches 0 of f of x plus h. So I put x plus h in for x there, minus f of x. It was minus a negative, so that's why we have plus there. We got rid of the denominators by multiplying by the common denominator, which is x plus h, okay, over x plus h. So when I took this first term times that, the x plus h canceled, so I just had the negative 2 times x. When I took this term times this numerator here, the x's cancel, so I have 2 times x plus h, and then I took h times x plus h. Distributed the 2 through, canceled the 2 x's, because it was negative 2x plus 2x, and then the h. The only term I had up here was 2h, so I could cancel that h. So I had 2 over x plus h. Now I'm going to take the limit. I haven't taken the limit yet, but I actually can put a 0 in for the h now. It says as h approaches 0, I'll put 0 there. So I have 2 over x times x. So that's 2 over x squared. That's my f prime of x. That'll give me the instantaneous rate of change or the slope of the tangent line anywhere on this graph. Well, they would like it at negative 1. 2 over negative 1 squared is 2 over 1 or 2. They would like it at 2. 2 over 2 squared is 2 over 4, which is a half. Okay, so we think the slope of the tangent line at negative 1 is 2. We think the slope of the tangent line at 2 is negative a half. Well, let's check that out. Let's graph it. If I graph our function, negative 2 over x, of course we have these asymptotes. It's our rational function here. Okay, when I put 1 in, I'm at negative 2. 2 in, I'm at negative 1. Okay, we get the idea. We know what rational functions look like. It's this loop-de-loop here. And on the other side, when I put negative 1 in, negative 2 over negative 1 is positive 2. Okay, when I put negative 2 in, I get positive 1. So I have something like this. All right, now they're telling me that the slope of the tangent line at negative 1 should be a positive 2. So let me look at where x is negative 1. We said, what, if I put negative 1 in here, I'm up at 2. And yeah, the slope looks like it's positive there. Positive 2 to be exact. They say that if I go to where x is 2, the slope of the tangent line should only be a half. So let's go to the point 2, 1. Yeah, that slope of that tangent line looks a little less steep than this, doesn't it? It's probably about a half. That's what we're finding when we find the slope of the tangent line. Okay? 2 over x squared was my derivative. Let's just graph that function. 2 over x squared, we still have an asymptote at 0. Okay, we still have the asymptote at 0. Whoops, and I have a horizontal asymptote at 0 as well. Sorry. However, when I put 1 in, 2 over 1's 2. When I put 2 in, I can't seem to mark that point. 2, 1, 2, 1, right? No, 1, 2, I mean. 2, we get a half. We still have similar, it's just, oh, I shouldn't be touching there. Maybe I should graph this on Desmos. The other side is positive 2. What I want you to see is, again, the derivative, the y coordinates of the derivative are always above the x-axis because of the x squared. It's 2 over x squared. Okay, this means that the derivative is always positive. That means the slope of the tangent line is always positive on our graph. Okay? A math professor found that after introducing his dog to a new brand of food, his weight began to increase. After X weeks on the new food, his weight was approximately given by this formula between 0 and 6. Find the rate of change of his weight after X weeks. Rate of change. We're talking about derivative when they say rate of change. So I want the limit as h approaches 0 of the square root of x plus h plus 40 minus the square root of x plus 40 all over h. Same process. You put x plus h in for x and then subtract the function. So now I have the limit as h approaches 0 of the square root of x plus h plus 40 minus the square root of x minus 40 all over h. Well, it's nice that those numbers go away. The limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Now we have different strategies in simplifying problems. We used the common denominator before, and in this one, we're going to use the conjugate. I'm going to multiply the top and bottom by x plus h plus square root of x. I'm trying to, simplify this so that I can put 0 in for h, and I can't do that yet because it gives me 0 in the denominator. So I use the strategy of multiplying by the conjugate. When I do that, my middle terms cancel. That's why we use the conjugate. It's that difference of two squares idea. Square root of x plus h times the square root of x plus h is x plus h. Square root of x plus h times square root of x minus square root of x plus times the square root of x plus h. That disappears. And then negative square root of x times square root of x, that's just minus x. And again, I'm just simply going to multiply my denominators together. Okay, I'm not going to distribute because I'm going to lose the fact that I can cancel my h's, maybe. Okay, x minus x. I'm going to take those away. The h's cancel, so I end up with 1 over the square root of x plus h plus the square root of x. And now I can put 0 in for x. 0 in for h. I get 1 over the square root of x plus the square root of x. That's 1 over 2 square roots of x. That will give me the slope of the tangent line, or the instantaneous rate of change, which is what we want in this problem, at any x that you tell me. So this tells us, for example, that after 4 weeks, his weight is square root of 4 plus 40, 42 pounds, right? That was his weight. At 4 weeks, we're at 42 pounds. But the weight is increasing at 1 over 2 square roots of 4. 1 over 2. Okay, I'm putting 4 in the derivative function. That's 1 over 2 times 2. So that's 1/4 of a pound per week. Okay, it's increasing at a rate of 1/4 of a pound per week. That's what a rate is. Okay, per something. Here we have costs. Okay. Cost in dollars to manufacture X calculators is given by this formula. We want the rate of change of the cost. So let's just find that general formula first. Limit as h approaches 0, negative 0.005 times x plus h squared plus 20 times x plus h plus 150. And then I'm going to subtract the cost function, which is negative 0.005x squared plus 20x plus 150. And of course, that'll all be over h. So I have the limit as h approaches 0 of negative 0.005. I'll take x plus h and square it. distribute my 20 through, distribute my negative through, so I have minus 20x minus 150. That's all over h, but I'm not going to write that yet, okay? The negative 0.005 x squared and the positive 0.005 x squared will go away. Of course, I have to take negative 0.005 times 2xh, okay, to get that. Negative 0.005 times 2xh will be negative 0.01 xh plus negative 0.005 h squared. It looks like the 20x's go away, the 150's go away, so I just have plus 20h here. Okay, and that's all over h. So the h does go into everything, good. And when it does, I just get negative 0.01x plus 20, because the h cancels here, but there's still one h there, and then when I put 0 in, that term zeroes out. Okay, so this is telling me the rate of change of cost per calculator gives us the marginal cost at 100. Okay, so I'll put 100 in my formula. See, I just put 100 in for x and got $10. Okay, oh, well, no, that was 1,000. When it was 100, I guess you got $19, but when it's 1,000, we get $10. So that's $10 per calculator. Okay, but when I'm producing 100, then it's $19 per calculator. Okay, the derivative does exist everywhere except where there's a corner or an asymptote or the function doesn't exist. Okay, but here the function exists, but it's such a sharp corner that I can't tell where the limit is. I can't tell what the tangent line is. Is it this line or is it this line? I mean, either one of them touches it just once. So therefore, since the limit's different on either end, the limit does not exist. The derivative exists everywhere except 0, right here at this corner. So you want to be careful. Anywhere there's a corner, you're not going to be able to have a derivative, okay? So a derivative exists if I have a continuous smooth curve. I can't have any sharp corners. I can't have any discontinuities like asymptotes or holes, okay? I also can't have a vertical tangent. This is getting so steep right here that a line that's tangent to it is vertical, which means it has an undefined slope, which means it has an undefined derivative there, okay? So the derivative does not exist if it's discontinuous, sharp corner, or has a vertical tangent, okay? If this is my function f of x and I want to trace the derivative, I notice that I have horizontal tangents here, 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 and here. What that means is the derivative is 0. So if I was going to graph the derivative, I know that right here at negative 3.5, it would be 0. Right here at negative, whatever this is, negative 1.1 is 0. Right here is 0. And here we go. All those places would be 0. Okay, because the slope of the tangent line at those points is 0. The slope of the tangent line there is 0. Then I just kind of want to look and see where I'm positive and where I'm negative as far as my slope. My slope is positive here, so I'm above the x-axis there. Right after here, notice my slope is negative, so I'm under the x-axis till I reach here. Then I'm positive again, then negative, then positive. Okay? So it's kind of something like that. Okay? All right. Try the homework on my math lab, and we'll see you in class.